All right, so the challenge was to parameterize the trivial tracking loop, this loop here, by decomposing it as a product of two non-trivial loops. So first, a couple more hints. So we want to remember that we're fixing a base orientation, namely this one. If you're thinking with Bala, this orientation here. And we're at every stamp, at every unit of time, the trivial loop's rotation state is a composition of two non-trivial loops rotation states, namely this one and this one. So remember that we're multiplying from right to, we're performing these from right to left, this multiplication, this product. So we're first performing this rotation here on the right, and next we're performing this rotation here on the left. So let's just see that animation again. The rotation on the right is they're both impossible to actually do with your head, but the rotation on the right is rotating with respect to this axis, this nose axis. This is the extent to which I can do it in real life. And the rotation on the left that you see is rotating the nose axis itself around. So let's just pay attention to those quickly. So the right is spinning with respect to the nose axis. The left is rotating the nose axis itself. And when we multiply those together, at every time step, we get the state of the trivial loop. So maybe I'll just rewind and see it again. So notice that at every time step, if we first perform the twist and then rotate the nose axis to wherever it's supposed to be based on this outer frame, we end up with the trivial loop. So at every time frame, for example here, I've rotated by 180, and then I've rotated by 180 my nose axis. And if you imagine taking this guy and rotating him by 180 degrees, you'll end up exactly with this state here. So at every timestamp, the same operation will work. We can take the state of this fellow, rotate it by this amount, and we'll get to this guy. So the trivial loop really is a decomposition in that way, at every instant of time. It's a product of these two rotations. Okay, so therefore, we can use quaternion multiplication to parameterize the loop. We can think of this rotation as the product of these two. If we can find the quaternion corresponding to this, it's just the quaternion corresponding to this times the quaternion corresponding to this. Well, we know the quaternions corresponding to these two at every unit of time, at every step of time, because we can parameterize these two rotation loops. They're just simple non-trivial loops, and we already saw how to parameterize them with quaternions. So this one on the right is just a y rotation loop, because I'm literally rotating with respect to the y-axis. I'm rotating my head with respect to the y-axis. This one here is just an x rotation loop. By the right-hand rule, an x-axis rotation should go in this direction, but I'm going in this direction. So this is really a negative x rotation loop. So a y rotation loop is parameterized by cosine of theta over 2 plus sine of theta over 2j. A negative x rotation loop is parameterized by cosine of theta over 2 minus sine of theta over 2i. So if we multiply these together, we should get the trivial loop, assuming that I'm not cheating you and that the trivial loop really is a product of this negative x rotation loop and this y rotation loop. So p of theta should be parameterized by this expression as theta goes from 0 to 2 pi. So using this, we can actually check it by plugging it into Blender, the 3D animation software, and seeing what we get. Okay, so that's pretty cool. We can really parameterize the trivial tracking loop as a product of two non-trivial loops. So as further exploration, can you describe other products of 360-degree rotation loops? Can you describe what you get if you take other non-trivial loops and multiply them together? And does the order of quaternion multiplication matter? For example, in the trivial loop we just saw, what if we multiplied these two loops in the opposite order? Would we get the same trivial tracking loop, or would we get something else? And what product loops can you perform with your own head? So this is a fun thing to explore on your own, especially if you are up for downloading Blender and trying this out, and just seeing if we take rotation loops about other axes and multiply them together, say a z rotation and an x rotation, or a negative x rotation and a z rotation, and multiply them in different orders, in different combinations. What do the products look like? Which ones can we perform with our own head, and are any of them particularly interesting? So that's something for you to try out.